All right, we're going to talk about some applications of the sine and cosine functions. We're going to be doing some modeling. So let's just go back to when we were graphing all of the different transformations of sine and cosine functions. We had these equations here, right? Where A is our amplitude, D is our vertical shift, B, so 2 pi divided by B is our period, right? Or we could say B equals 2 pi divided by period, either way. And our phase shift is C divided by B, right? If we factor B out of both of these, we end up with C divided by B as our phase shift here. Okay, so it's not just C, it's that phase shift. It's that ratio between C and B. This is a B, not a D. I wrote it wrong. Okay, so let's look at the kinds of problems that we can use to sine and cosine to model functions with. There's a lot of periodic things in the world, things like weather and tide patterns and actual waves like sound waves or the way a guitar string vibrates, all kinds of things, have a periodic element to them, and sine and cosine are the key to modeling them. So let's look at this data. The average monthly temperatures for a small town in Oregon are given here. Find a sinusoidal function of this form that fits the data and sketch the graph. And this makes sense because weather is periodic, right? Winter's cold, summer's warm. All right, so we've got this data. And the other thing about real life data is sometimes it's kind of messy, right? It doesn't always we're gonna have things that kind of fit it, but aren't necessarily going to fit every exact point. So we're gonna have to do the best we can. So let's see, where do we want to start here? So in January, so let's just kind of get a rough idea of what this is going to look like. Right, in January, we're down here at so we're actually up here, right? We're going to be at if this is 40, and it looks like the highest it gets is between 40 and 70. Right, it's Oregon, so it never gets especially warm. So we're going to start here. So this is January. And the highest it's going to get is in August. So let's say here's August. It's going to be almost 70, right? And here it just keeps getting a little bit warmer. And then it gets cold again in December, right? So the coldest it gets, it looks like, is January. And the warmest it gets is July and August. So is that going to work? I mean, we definitely are going to want to have a period of 12 months, right? I mean, it's not like years are longer or shorter than that. That's what the period of the weather is. So this is going to be a perfect fit. So first of all, let's see. Let's maybe find what our B function is, right? Our period is going to be 12 months. So that's going to equal 2 pi divided by B. So B is going to be 2 pi divided by 12, or pi sixths, right? Our amplitude, let's think. It looks like it's going to go from between about 42, let's say 42 up to 69, something like that. So the amplitude, we're going to go from 69 to 42. That's from max to our min. And remember, amplitude is going to be that divided by 2. So what do we get here? Like 27 divided by 2. So 13.5. Right? This is just rough. And are we going to shift it at all? Probably not. If January, if it's going to look something like that, let's say, this is going to be, let's just not shift it to make it easy. Right? It's gonna peak somewhere in the middle. It starts at the beginning and end of the year. It's at its coldest. So let's not shift it. And what kind of function would make sense to use here? Well, it looks like if it starts at the bottom and halfway through it's at the top and ends at the bottom, looks like maybe a negative cosine. So let's put this all together. We're going to have y equals negative 13.5 times cosine. Our b value we decided was pi 6 t, and we're not shifting it, we decided. And then how are we going to vertically shift it? Well, what's halfway between this? If we were going for between 42 and 69, we'll have to add this to the lower end, right? 42 plus 13 is going to be 55.5. Something like that, right? And we could put in some data to see how this works. We could graph it. Maybe we decide, maybe we should shift it just a little bit one way or the other horizontally. But this is the main idea, right? We kind of found, this is easy, right? We definitely know what the period we want to be. The amplitude is pretty easy. I guess the question is, when we look at this, if the maximum values are in July and August and the minimum values are not exactly, it's like 1, 2, 3, 4, 5 months away from that. So this might model that the maximum is a little bit earlier than it actually is, like maybe in June or July, which isn't exactly accurate. So modeling never works out perfectly, right? You're just looking for best fit sort of things. Okay, let's look at another one. Let's see if I just turn this sideways. How's that going to work? All right, what about this? The hour hand of the large clock measures 24 inches in length. At noon, the tip of the hour hand is 30 inches from the ceiling. Okay, so we've got a clock here and we've got a ceiling up here. And at noon, this is obviously pointing straight up, right? At noon, and this is 24 inches. And at noon, it's 30 inches from the ceiling. And at 3 p.m., so over here, the tip is 54 inches from the ceiling, which makes sense. And at 6 p.m., 78 inches. Does that work? 30 plus 48, yeah. At 9 p.m., it's again 54 inches from the ceiling, and at midnight, it's at its original positions. Let y equal the distance from the tip of the hour hand to the ceiling x hours after noon. So this is a little bit contrived, right? Why would you actually want to model this? But here we are in a trig class, so we're going to do it. So let's. I think a good place to start with these is always with a little sketch of your graph to give you an idea of what kind of trig function you're going to use, what your vertical shift is going to look like. So here we are at noon, and then here we are at midnight, right? And at noon, we are 30 inches away. And at midnight, we're, again, 30 inches away. Then at 3 p.m., so here's 3, 6, 9, let's say. At 3 p.m., they tell us we're 54 inches. So let's say 54. We're up here. And at 6 p.m., obviously did not draw this very well. At 6 p.m., we're all the way up here. And then at 9 p.m., we're back here. All right, so our graph is going to look like that, except not be wonky. Okay, so we're starting at our lowest point, and halfway through we're at our highest point, and then we're ending at our lowest point again. So this looks like a cosine curve, a negative cosine curve, right? Okay, so let's think of our different, what's our amplitude? Our amplitude is, first of all, I guess we could say, what's our midline? Our midline is going to be 54, right? Halfway between the top and the bottom. So that's going to be our vertical shift. We know we're going to have a minus here. Our amplitude, we're going from 54 to 30 up to 78. So that's a difference of 24. So it's going to be minus 24 cosine. And then here we'll have our vertical shift of plus 54. And I guess the question is, what's our period, right? Our period is 12 hours. So our b value is going to be 2 pi divided by 12 hours, or pi 6 again. So pi 6 t, right? Where t would be time, or I guess x. They told us to use x. Okay. And our graph, they ask us to graph it. We could do a better job. You could do a better job. But here's the general idea, right? Okay, let's do another one. Tides. The height of the tide in a small beach town is measured along a seawall. Water level oscillates between 7 feet and 15 feet. Okay, so here's 7, here's 15. On a particular day, low tide occurred at 6 a.m. So let's say that this is 6 a.m. And high tide occurred at noon. Approximately every 12 hours, this cycle repeats. So let's say they said low tide is at 6 a.m. and high tide is at noon. So then at every 12 hours, the cycle repeats. So let's say again at 6 p.m., we're going to be down here at 7 feet again, right? So it's going to look something like this. So again, it looks like a negative cosine function. They're not always negative cosine functions, just these few examples. So we're going to have something of the form y equals negative. Let's see, what's our amplitude? Well, first of all, what's our vertical shift? So halfway between these, looks like the distance between them is 8, right? So halfway between is going to be 11, right? So our vertical shift, I'm going to put over here, is plus 11. And our amplitude is how much it goes. It goes between that vertical shift and the max or min. So it looks like 4, right? So we'll say minus 4 cosine. Our period is 12 hours. Again, this is a coincidence. Like every period obviously isn't 12 hours. But again, if b is going to be 2 pi divided by 12, so again, we're going to have pi 6 there. Pi 6 times, do they tell us what variable they want us to use? No, let's just say t. Okay. Let's do another one. Blood pressure. So they give us the equation in this case where f of t represents the blood pressure at time t measured in minutes. Interpret the function in terms of the period and frequency. Sketch the graph and find the blood pressure reading. I don't know what that means. Find the blood pressure reading. We'll sketch the graph. All right, so let's think. This means, so the blood pressure, the amplitude is 20. So it's normally 100, right? The midline is 100. So let's say if this is 100, it might go down to 80 or it might go up to 120. What's the period? Well, the period, so B equals 2 pi divided by the period. So the period is going to be 2 pi divided by 160 pi. So 1 over 80 is the period in minutes. Okay, so this is like as our heart is beating, our blood pressure is changing in our body, right? So like a little bit less than every second, our blood pressure is changing. It's getting bigger and smaller, okay? And I bet there's like ways to interpret that. If you were in a biology class, you'd know what it was, but I don't know what that is. But here's how it changes. Here's how often it changes for this one person. Okay, so the period, so here's in minutes, right? So this is in minutes, 1 over 80 minutes. So a little bit less than a second is the whole cycle. And it's like a sine curve. So it's going to start here. Let's see, halfway through, let's say that's 1 over 160. It's going to be back at that baseline. And at the end, it's going to be back at that baseline. And halfway through, what is that? 1 over 130 or 320. And this would be, let's see, whatever that is. We can figure this out. 160 plus, let's see, it's a quarter of the way is 1 over 320 plus 1 over 160. So it's going to be 3 over 320. It's going to be down here, and here it's going to be up here, and it's going to look roughly like this. Okay. So a little bit more than once a second, our blood pressure, the average person's blood pressure, fluctuates between 80 and 120. Okay. So as our heart beats, like about once a second or so, I guess, a little bit more than once a second, which seems kind of a lot. Does that seem like a lot? As the blood goes through our body, our blood pressure changes, right? Okay. All right, so now let's think of this combining some functions, okay? We're going to talk about damped harmonic motion. So this is the case if, for example, you have a spring. So think about if you pull a weight down, it goes up and down, and that follows a periodic function, right, as it goes up and down. But you have seen a spring. It doesn't go forever, right? It starts going down, and then it goes a little bit less, and then a little bit less, and then a little bit less, right? And the way it gets damped, we call that damping, okay? If the magnitude gets less of something, like, or if a ball was bouncing, right? So some things like ocean tides, they don't damp, right? They're always the same kind of magnitude. I mean, I know they change a little bit throughout the month, but it's not like over time they get sort of tired, right? The way a spring bouncing or a spring oscillating or a ball bouncing would get less and less over time. So something that gets less and less over time, we call that damped harmonic motion. So harmonic motion is a periodic function that we could model using a sine or cosine curve. Damped harmonic motion is something when it gets less and less over time. So here's what the equation is going to look like. It's our regular equation, except it has this term in front, e, and it's a little bit hard for you to see, I can tell. What if I move it here? It's easier to read. E to the minus ct, e to the minus ct. So we have a exponential function here multiplied by our periodic function. Okay, so let's do an example where we would figure out what that was. All right, so we have a spring, 10 inches in natural length is compressed by 5 inches and released. Okay, so it's normally hanging at 10 inches. So let's just think about this. So here's 10. It's compressed by 5 inches and released. So let's see, how do we want to measure this? Let's just think of what this looks like. If we have our measurement here, here's our spring. Okay. And how are we going to measure this? So normally it's 10 inches. So here's 10 inches. Okay. We can measure this two ways. Do we want to measure from the board or ceiling or whatever that it's attached from? Or do we want to measure from down here? Either way, it's not clear how they want us to do that. So we can just decide. It's compressed by 5 inches. Let's say we're going to measure from up here. So let's say this is 5. Okay, we've compressed it to 5 and then let it go. There's some symmetry here. So it's going to go up to here and then kind of oscillate between 5 and 15, and then get less and less and less, right? Okay, so our graph is going to look a little bit opposite from our drawing here. If we wanted to measure from down here, we could do it that way, but we can think this through. So at time 0, we're here at 5, right? Okay, so it oscillates once every 3 seconds. Okay, so we know it's going to look something like it's going to go up and then down, and then back up and down and back up and down. That period is going to be 3 seconds. Okay. And it tells us its amplitude decreases by 30% every second. All right, so we've got a few equations to think about here. One is we need to find this. Well, first of all, we have to decide, are we going to use cosine or sine? I mean, we're starting compressed. We're starting at the bottom, and then it goes up and then back down. So this looks like a negative cosine to me. So our equation is going to look something like negative a e to the minus, or let's just say kt. Okay, this is going to turn out to be a negative number, times cosine. If our period is 3 seconds, our B value is 2 pi divided by our period. So 2 pi thirds times t. Okay, so we need to figure out what this A value is and also what this K value is. Our A is our amplitude still, so this is going to be 5. Right, so how should I write that? This is 5. Okay, now how are we going to find what our K value is? We're going to use this information. The amplitude decreases by 30% every second. All right, so we got to think back to our exponential functions. We're going to have something of the form y equals a e to the kt. Okay, and we want to find out what k is. Our a value is our initial amplitude, which is 5. So we can start with 5 e to the kt. And if you remember back to last semester, how do we find this value? We think of a second point. Okay, well, what is our second point going to be? We know that when t is 1, what's our amplitude? Well, it decreases by 30%, so it's going to be 0.7 times 5. Let me go write it like that so it's more clear. 0.7 times 5, because it's decreased by 30%. Okay, we don't even have to figure out what that number is. If we can plug this point in, so we can say 0.7 times 5 equals 5 e to the kt. Well, we can divide by 5s, and we just have 0.7 equals e to the kt. So we take the natural logs of both sides. Right? Natural log of this, the e goes away, and we're just left with the exponent. Oh, and we forgot to put in t. T is 1. So natural log of k is the natural log of 7, or 0.7, sorry. We can find out that number by putting in our calculator, or we can just leave it like this. So we go back to our original equation. It's going to look like y equals minus 5 e to the natural log of 0.7 times t times cosine of 2 pi thirds times t. Okay, so for damped harmonic motion, a little bit more complicated. We still figured out the B value the normal way. We found the amplitude the normal way. We figured out which equation we wanted to use to model it by kind of doing this quick little sketch. And then we solved this is like a little side project, right? We had to find what our K value was for the exponential part of the equation. Okay. And the last thing I wanted to show you, and I don't think you have any homework problems about this, but I just wanted to show you this because it's kind of cool. What happens if you multiply, if you have oscillating cosine curve? So it's not damped, but it's getting bigger and smaller and bigger and smaller. This can happen a lot with waveforms. Okay, so if you ever get into electrical engineering, you're going to look at things look like this. So we got two cosine curves multiplied together, right? So we've got our inside one, the blue one here, and our pink one is sort of the outside function. And the result is that it looks like this, right? We have something that's going back and forth periodically, but then there's a bigger waveform that's making it get bigger and smaller. This is kind of just like for your information. You don't have any questions like this or need to recreate this, but I just wanted you to see this because you might see this again in your career if you, like I said, do something like electrical engineering.